In this video, we want to solve this expression. To prove by mathematical induction that the statement summation k to equal to 1 up to n 1 over 2 to the power of k equal to 2 to the power of 1 minus 1 all over 2 to the power of n is true for all positive integers of n. So k starts from 1 in this statement. K starts from 1 and tends to n. Alright, so that essentially means that this is what that statement means. We have 1, 2, 3 up to n. That's what it means. So at this point, we're going to check for when k is equal to 1, what will happen to this left hand side. We're working on the left hand side only. So if when k is equal to 1, this means that we'll be having 1 over 2 to the power of 1. Anywhere you see k, is substitute 1. And what will be the result to that? 1 over 2 to the power of 1 is same thing as 1 over 2. We're also going to check for when k is equal to 2, and then that will be 1 over 2 all to the power of 2. Let me break this down. Of course, you know when we have anything squared like a squared, it means a times a. Similarly, 1 over 2 squared means 1 over 2 times 1 over 2. So 1 times 1 will give you 1 all over 2 times 2, 4. So this will be the result. We also check for when k is equal to 3. You can do same for when k is equal to 4 and as the case may be. So when it's equal to 3, it means we are having this thing like 3 times. And of course, when you have it 3 times, 1 times 1 times 1 will still give you 1. And 2 times 2 times 2 will give you 8. Alright, because 2 times 2 is 4, 4 times 2, that is 8. So it means that the series will become, in place of this Zigma summation, we then have 1 over 2 plus 1 over 4 plus 1 over 8 plus to infinity plus, then we have this series starting with 1 over, because we don't know what point it will end, so we just end it with 1 over 2 up to the power of k. Alright, and this will give us what we have at the right hand side, which is 2 to the power of n minus 1 all over 2 to the power of n. Okay, so this is when we will start, this is where we start solving the problem. And in step 1, we want to show that n equal to 1 is true. We want to show that n equal to 1 is true. So what do we need to do first? We have to prove by induction. Already from this summation, notice that k is equal to 1. If you make the statement, if k is equal to 1, and here you are now having n equal to 1, then by induction, it means that k will be equal to n, which is equal to 1. What this literally means is that wherever you see n, you can put 1. Whenever you see k, you can put 1, because of this statement we just made, and that is built upon this foundation. Alright, so if that is well articulated, then from the left hand side, we'll be having 1 over 2 all to the power of k, and the k will be replaced with 1. So we have 1 over 2 all raised to the power of 1, and the answer is 1 over 2. Let's also work on the right hand side. From the right hand side, we're having 2 to the power of n minus 1 all over 2 to the power of n. So what will become of this? Anywhere you see n, you put 1. So when we plug 1 here, minus 1 all over 2 to the power of 1, then the result will be 2 raised to the power of 1 is 2. 2 minus 1 is 1. All over 2 to the power of 1 is still 2. So you can see that the left hand side is giving us exactly what we have at the right hand side. So since left hand side is equal to the right hand side, then n equal to 1 is true. Alright, so we are done for that first step. Now what about the second step? The second step is the step we make assumption. So we're going to assume that n equal to k is true. Right. In this case, from the left hand side, we will have this statement: 1 over 2 plus 1 over 4 plus 1 over 8 plus up to 1 over 2 to the power of k. Of course, what we have there is k, so there's no point we can change it or make it double k. K is already there. If it were to be n, you would have changed it to k, but since it is k, you just leave it that way. On the right hand side too, anywhere you see n there, you replace it with k. So we have this to be equal to the right hand side, which is 2 to the power of k minus 1 all over 2 to the power of k. So this is the point where you're going to leave this expression and you just make an assumption. I say therefore n, we just made an assumption, n equal to k is true for all integers. Right, for all integers n. So this is the last point we're going to enter. The last step is the step 3, which we prove that the right hand side is always equal to the left hand side. And this is essentially where some students usually have issue. But let's see how we can break the barrier also with this question. I've always told us that if you're having a big challenge on the recent problem we are solving, that you could use the link in the description to check the first, second, third videos. That way you have a better understanding, right, of the concept. So here we want to show that n equal to k plus 1 is true. So what do we need to do? We build it upon this step 2. So copy down what you're having there, which is 1 over 2 plus 1 over 4 plus 1 over 8 plus the next thing is up to 1 over 2 to the power of k plus, this will increase by 1. So you have 1 over 2 to k plus 1. Alright. So the right hand side, anywhere you see k, you just change it to k plus 1 minus 1 all over 2 to the power of k plus 1. So that's what you need to do on this step 3. So but then notice that the whole of this, from this point down to this point, look at it here, from this point down to this point, which is essentially what we have here, we mark here, gave us what you're having at the left hand side. So I'm going to replace the whole of this for this, because the whole of this is equal to this. So in place of this, in place of the whole of this, I will replace it with this. So I have 2 to the power of k minus 1 all over 2 to the power of k. This will be added to this one we have in here, which is 1 over 2 k plus raised to the power of k plus 1. The whole of this will be equal to what we have at the right hand side, 2 to the power of k plus 1 minus 1 all over 2 to the power of k plus 1. Alright, so this is where you're going to do some sort of mathematics. The mathematics you want to do is essentially about making sure that what you have at the left hand side corresponds to what you have at the right hand side. That's just the basic thing we want to play with. So that means we'll just leave the right hand side the way it is and then work on the left hand side. So we say from the left hand side, what do we need to do? So let's start up the mathematics. So the first thing the first approach is to write down this expression of the left hand side, 2 to the power of k minus 1 all over 2 to the power of k plus Okay, I want to start with this. 1 over 2 all to the power of this means that 1 will share from this and 2 will also share from this. So you can rewrite it to be 1 to the power of k plus 1 all over 2 to the power of k plus 1. That's what this thing means, because since two of them are k plus 1, you can just factor 1 and then put this 1 over 2 in the bracket. So this and this is the same thing. I repeated this one. So what will this expression give us? Watch. This is the same thing as writing this left hand side is still 2 to the power of k minus 1 all over 2 to the power of k plus, you know that 1 to the power of any number is still that number. So was still 1. 1 to the power of 500 is still 1. 1 to the power of a is still 1. So 1 to the power of k plus 1 is still going to be 1 all over what you're having at denominator, which is 2 to the power of k plus 1. All of that makes sense. All right, let's make more deduction. But there's something I want you to take note of. According to product rule of indices, if you have a to the power of m times a to the power of n, notice that whenever the base is the same, you just take one of them and you add the power. Do not forget this law of indices, because we're going to do some sort of a breakdown process using the law. So the next thing I'm going to do is to take the LCM of this denominator. What is the LCM? The LCM of 2 to the power of k and 2 to the power of k plus 1 is multiplying two of them together. So you have 2 to the power of k into 2 to the power of k plus 1. So that's the LCM. Of course, if this goes into this, if this goes into the whole of this one will cancel out with this one. And then this is what will remain in. This one now multiplied by the numerator is 2 to the power of k plus 1 multiplies by the numerator 2 to the power of k minus 1. Please take note, this minus is not up here the way this plus is. It's just down from the original equation. Plus, this will cancel out with this one, remaining 2 to the power of k. 2 to the power of k times 1 will be 2 to the power of k. Alright, so what is the next step? The next step is this. We're going to break this down. This thing is same thing as having 2 to the power of k multiplies 2 to the power of 1. According to indices, look at it. Even if I use times, please, this dot signifies multiplication. So because the bases are the same, we just have the common base and add the power k plus 1, which is this rule. Alright, this rule is what I just applied here. It's what I applied there. So I had to split this one to this form because it was this that gave us this. And we have reasons for doing that, because we're essentially simplifying this so that we can get this right hand side. So you put this other one into the brackets as usual, 2 to the power of k minus 1, then plus the k plus the 2 to the power of k you have already. This will divide what you have at the denominator, which is 2 to the power of k into 2 to the power of k plus 1. So from the numerator, you will notice that 2 to the power of k and 2 to the power of k, they are common. So because they are common, I will just pick out one of it and then I will open a parenthesis. So if you remove this 2 to the power of k, what will be remaining here is 2 to the power of 1 into 2 to the power of k minus 1 plus, if you remove this 2 to the power of k, what will be remaining here is 1, not 0, because this multiplies by this will give us back this whole thing, and this 2 to the power of k multiplies by 1 will still give us this. So at this point we can divide both sides, or f the whole of the expression, by 2 to the power of k into 2 to the power of k plus 1. So what will now be the next step? At this point you can see that 2 to the power of k will cancel out. Then here, this 2 is going to distribute into this bracket. How do we do that? 2 to the power of 1 times 2 to the power of k is the same thing as 2 to the power of 1 plus k. according to indices, because the bases are the same, you add the power. All right, and then this 2 to the power of 1 will multiply by minus 1, so to give us 2 to the power of minus 2 to the power of 1, then plus the 1 that is remaining here. This will be over 2 to the power of k plus 1. All right, so the next thing is this: 2 to the power of 1 plus k is the same thing as 2 to the power of k plus 1. Because it is positive, you can always tweak those parameters there. So this will be minus 2 to the power of 1 is the same thing as 2. Then minus 2 plus 1 should give us minus 1. All right, all over 2 to the power of k plus 1. Now this is where we will end it. Now check the right hand side of this expression. Look at what we're having at the right hand side. We're having 2 to the power of k plus 1 minus 1 all over 2 to the power of k plus 1. This is the same thing we're having: 2 to the power of k plus 1 minus 1 all over 2 to the power of k plus 1. So since the left hand side is equal to the right hand side, then n equal to k plus 1 is true for all positive integers. And if you like this video, please like and subscribe.